Today, we're going to work on this in-class assignment together, but we're going to take it a step further. And instead of just writing our equations, we are going to effectively write the entire set, and then I'm going to show you guys how to use complex numbers in MathCAD, because there are some homework problems and stuff like that you definitely need to use MathCAD for. And then once we wrap that up, we're going to be working on the laboratory assignment. All right. So I'm going to let you guys choose, because in problem one, we're asked to use nodal. Problem two, we're asked to use mesh. Do you have any preference which one of these two we're going to do, or which one do you feel like you need more refresher on how to use? My best guess would be nodal analysis, because most of you guys seem to like to use mesh for everything. All right, so we are going to analyze this circuit using nodal analysis, and the process for this is effectively the exact same as it was when we did nodal analysis for the better part of 6 weeks ago, right? So the first thing that we are going to do is identify our nodes, set our ground. All of that kind of stuff has been done for us, right? So we can see that all of our nodes are labeled with phasor nodal voltages. Our ground has been chosen to be the bottommost node. And so now we're going to start on our controlling variable relationships, right? So let's just put those here. So we have two different controlling variables. We have this current Ix, and we have this voltage Vx up here, and each of those control a dependent source. So let's start with our equation for Vx. So can anybody tell me how I would express my phasor voltage Vx in terms of my nodal voltages? Anybody remember how to do that? So just as a refresher, it's always simply the nodal voltage associated with the positive polarity terminal minus the nodal voltage associated with the negative polarity terminal. So the positive polarity terminal is V2, and the negative polarity terminal is V1. So we would simply have the relationship Vx is equal to V2 minus V1. For this current Ix here, there are a couple of different ways that we could do this. So this is the current that's flowing through a voltage source, which means that we're not going to be able to do any, node the current originates from minus node the current is flowing to over a resistance, because we don't have a resistance, right? So we are going to have to apply either Kirchhoff's current law at node 5. So that would be this current flowing in plus this current flowing in plus this current flowing in, add together to make Ix. So that's one way, and we'll write that equation in a moment. And then the other option we would have is recognizing that Ix flows through that dependent source. So this is Ix as well. And so we could say that it is equal to this current flowing up plus this current flowing down. So either KCL at node 5 or KCL at node 6 gives us a relationship for solving for Ix, or defining Ix in terms of our nodal voltages. Either of them are correct. So if I were doing this just by myself, I would do the KCL at node 6 version, but I'm going to explain both of them just in case you guys are wondering. Okay. So let's start with the KCL at node 5, right? So Ix is flowing out, and that is just going to be the sum, equal to the sum of all of the currents that are flowing in. So what would my current flowing down through my 7 ohm resistor be expressed as? So it's not going to be V2 over 7, V2 minus V5 over 7, thank you. And then my current flowing from left to right through my minus J5 ohm capacitance. So V4 minus V5 over minus J4 ohms, okay. And then my current flowing up through the 4 ohm resistor. Negative V5 over 4 ohms. Absolutely correct. If we're applying KCL at node 6, what's my current flowing up through the current source? 2 angle 0. Okay, so I'm just going to put over here, or Ix is equal to 2 angle 0 degrees amps plus, and then what's the current flowing down through the J6 ohm inductance? V6 over J6, thank you.
Second part of the first one, would it be over negative J5?
Oh, sorry, you're correct. That is definitely over negative J5. I just wrote it down wrong. Thank you for that, Ashton. Goodness, because that is a minus J5 ohm capacitance, not a minus J4. So thank you very much for catching that mistake. So when we're setting up our system of equations in MathCAD, we would use either of these two equations for Ix. We would not use both because there's literally no point in using both. Okay. So now that we have our controlling variable relationships done, we're going to write our voltage relationship equations. So anytime that we have a voltage source, we're going to have voltage relationships. So I've got this voltage source right here and this voltage source right here. So let's start with the one on the left, okay? So that would look like 12 angle 0 degrees volts is equal to what? V1 minus V3, absolutely right. So exact same rules for how we defined Vx. It's the nodal voltage associated with the positive polarity terminal minus the nodal voltage associated with the negative polarity terminal, okay? Now we're going to do the current, excuse me, the voltage source over here on the right. So we would have 3 Ix is equal to what? V5 minus V6, absolutely. Those are our only voltage sources, so we are good to go there. So now I believe our next step would be to move on to our KCL at our supernode equations, right? So I'm just going to kind of draw a loop around our supernodes. Both of our voltage sources in this case are supernodes, and neither of them contain ground. So we're going to have to write KCL equations for both of them. So the currents leaving supernode 1, 3 are going to be this guy flowing down through the minus J2 ohm resistor, this guy flowing to the right through the 1 ohm resistor, this guy flowing down through the J3 ohm resistor. Our currents leaving supernode 5, 6 are going to be this current flowing up through the 7 ohm resistor, this current flowing to the left through the minus J5 ohm capacitor, this current flowing down through the 4 ohm resistor, this current flowing up through the current source, and this current flowing down through the J6 ohm resistor. Okay. So let's start with KCL at supernode 1, 3. So the current flowing down through the minus J2 ohm capacitance would be what? V1 minus V4 over minus J2 ohms. Absolutely right. And then we have a current flowing to the right through our 1 ohm resistor. What's that going to be? Yeah, V3 minus V4 over 1 ohms. And lastly, our current flowing down to our J3 ohm inductance. V3 over J3. And we set this equal to 0. And let's do KCL at supernode 5, 6 over here to the right-hand side. So our current flowing up through our 7 ohm resistor. Thank you for that. So V5 minus V2 over 7. Our current flowing to the left through our minus J5 ohm capacitance. Thank you. So V5 minus V4 over minus J5. Our current flowing down through the 4 ohm resistor. V5 over 4. Thank you. Our current flowing up through our current source, 2 angle 0 amps. And our current flowing down through the J6 ohm resistor is once again just V6 over J6 ohms. Okay. All right, so what do we have left? So that's going to be our Kirchhoff's current law equations at all of our remaining non-reference nodes, right? So if I'm not mistaken, so we have node 1 and 3 taken care of from that supernode relationship. We have node 5 and 6 taken care of with that supernode relationship. So I think all we're left with is KCL at node 2 and KCL at node 4. Okay. So KCL at 2 is going to be this current plus this current, right? So what's the current flowing down through the 7 ohm resistor? Again, V2 minus V5 over 7. And then the current flowing down through the current source, negative 2 angle 0 degrees amps. Thank you all. And then lastly, we're going to have KCL at 4 over here. And so that is going to be this guy plus this guy plus this guy plus this guy. So let's start with the current flowing up through the minus J2 ohm capacitance. So V4 minus V1 over minus J2 ohms. The current flowing to the left through the 1 ohm resistor. V4 minus V3 over 1 ohms. The current flowing down through our dependent source, minus 2Vx. Thank you for that. And then lastly, the current flowing to the right through our minus J5 ohm capacitance. So V4 minus V5 over minus J5 ohms. Set all of this equal to 0. All right, so it looks like we have 1, 2, 3, 4, 5, 6, 7, 8 equations, and we have 8 unknown quantities. So our 6 nodal voltages, Vx and Ix. So it seems like we have everything set up. Quite obviously, we would never attempt to do this by hand because even if this didn't involve complex numbers, this would still be a huge pain in the butt. But because it also includes complex numbers, this is not a set of matrices that I ever want to touch with my hands. So instead, we're going to use MathCAD. So the process is going to be fairly similar. We're going to have to use a solve block for this. And so I'm going to define all of my variables. And I don't know that I necessarily have to do this, but I choose to define my variables as complex numbers themselves, right? So I might have something, sorry, caps lock was on, like V1 is equal to, and so I'm going to put this in parentheses, 1, and then I need to do angle 0 degrees. So just to show you guys a quick thing here, if you go into the operators and you go down to the engineering section, we can see that we can get the angle operator from this menu, or we can use the keyboard shortcut Control-Shift-P to do the angle operator. So that's how I'm going to do it every single time. So 1, Control-Shift-P, 0. Now, technically speaking, we could leave this alone, but the default angle for MathCAD is in radians. and I prefer to work in degrees. If we look here at our engineering operators again, and we look at the degree symbol, notice there is no keyboard shortcut for this. So if we want this nice, neat symbol, we would have to click this every time. Well, I am far too lazy to do that. So instead, if I type in DEG, it interprets that as the same thing as a degree symbol, okay? So I have 1 angle 0 degrees, and then outside of these parentheses, I'm going to explicitly multiply by a unit of a volt, which is just the letter V, okay? So here, when we're manipulating complex numbers, it is going to be critically important for us to explicitly multiply and not let MathCAD really have any opportunity to confuse what we're trying to do, or things are going to go horribly awry very, very quickly. So anytime I'm assigning a unit or anything like that, I'm going to explicitly multiply. I'm going to be very judicious about how I apply my parentheses and all that kind of stuff, because it's so easy to get errors in our system. All right, so I'm going to go ahead and just keep this train rolling and declare all my other variables. So 1 angle 0 degrees, volts for V2, 1 angle 0 degrees, volts for V3, 1 angle 0 degrees, volts for V4, and V5, and V6, and Vx, and for Ix, or excuse me, for Iy, I think, is it Ix or Iy? Oh, I used the X twice. My apologies. Same thing, 1 angle 0 degrees, but now I'm going to use amps, obviously, because it's a current. So I've declared my 8 different variables. Then I'm going to go down into my constraints section, and this is where I'm going to put in all of those equations exactly like we did before. So we have to be kind of careful. So let's pop back over here real quick. So my first equation is simply Vx is equal to V2 minus V1, so nothing to really worry about there. So Vx control equal V2 minus V1. For my Ix equation, I'm going to use that second relationship just because it's less stuff to type. So that's going to be 2 angle 0 degrees amps plus V6, that is not a 6, over J6 ohms. Okay, so if I type in J6, that J is italicized. And so that means it's considering that to be a variable, which I do not want. So I have to reverse the order, very similar to what you guys have to do on your calculator. So instead of putting J6, you put in 6J or 6I in your calculators, and I do the same thing, okay? So notice right now that the J is no longer italicized. So it is, MathCAD is correctly interpreting that as the square root of -1. If I were to put a capital omega, it reverts it to italicized. So now it's thinking that there is a variable J omega, which does not exist. So as I said earlier, 6J, and now I have to explicitly multiply by the unit in order for it to interpret it exactly how I want it. So this is an impedance having a magnitude of, 6J, and its units is ohms. You guys have a question? Oh, because I put the wrong one. So that should be a control equal. Yep. Just a simple mistake. So in the constraint section, they should all be control equal. Thank you for catching that, or it would have wound up giving me an error in a little bit. All right, so now we have our voltage relationships to do. So I think the first one was something like 12 angle 0 degrees volts will be control equals to, and then something I can't remember, V1 minus V3. And then the next one was 3IX. So I want to take a look at this just really quickly. So this is a current controlled voltage source, which means that the 3, that scaling factor, has implied units of volts per amp. So I'm going to make sure to put that in. Otherwise, I'm going to get a unit error in MathCAD. So 3 volts per amp times IX is control equal to V5 minus V6. There we go. And now I'm into my KCL equations. So just giving myself more space, we're going to start off with KCL at our supernodes. So for supernode 1, 3, that is V1 minus V4 over minus J2. So V1 minus V4 over minus 2J times an ohm. Oh, crap. Okay, that's fine. My next term is V3 minus V4 over 1 ohm. And my next term is V3 over J3. So 3J times an ohm. And control equals to 0. My next equation is KCL at supernode 5, 6. Oops, that's the wrong thing. So V5 minus V2 over 7. And then I have V5 minus V4 over minus J5. Then I have V5 over 4. Shit. Then I have minus 2 angle 0 degrees amps plus V6 over 6J ohms is control equal to 0. And now I've just got my 2 regular KCL equations. So let me remind myself of what those look like. So V2 minus V5 over 7. Minus 2 angle 0 degrees, oops. Amps is control equal to 0. And then my last equation is V4 minus V1 over minus J2. I'm sorry, what? Oh, so I'll show you that real quick. So this term was over what? Negative 2J times, all right, so capital W and then control G. So capital, I think I explained this way back when, but effectively control G just converts a character into Greek. And so since lowercase w looks like lowercase omega, capital W converts into capital omega because that's the logic that MathCAD uses for whatever asinine reason. So if you were too lazy to learn these things, which, you know, I have to use them all the time, which is why they're seared into my memory. If you bring up the symbols menu, you could literally just go through and find the uppercase omega thing here, and it tells you capital omega and then control G, or excuse me, capital W and then control G. All right, next term. V4 minus V3 over 1 ohm. Minus 2 Vx. So actually, let's go back up here and look. So this is a voltage controlled current source, which means that 2 has implied units of amps per volt. So I'm going to have minus 2 amps per volt times Vx. Sorry, my cursor keeps getting lost. Then I have plus V4 minus V5 over minus J5. So plus V4 minus V5. Minus 5J times omega is equal to 0. All right. So there's my 8 equations. Let me scroll down some more so I can put my matrix down. This is technically optional, but I think it is very good practice, particularly when we're going to have to start manipulating these things in calculating powers. Oop, I did not want it there. Sorry. I want my matrix down here. My apologies. And so V1, 2, 3, 4, 5, 6, X, IX, find V1, V2, V3, V4, V5, V6, Vx, Ix is equal to this. All right, so let's look at this just really quickly. So by default, MathCAD is going to give us our answers in rectangular form using I as the imaginary operator. I don't particularly like this, so I just want to show you guys here. If you go into the math formatting tab and you look at this bottom right hand option under results, it lets us choose how we want our complex values returned to us. And we have several different options. So the top option is in rectangular form using I as the imaginary operator. The next option is in rectangular form using J as the imaginary operator. So this was built for electrical engineers to use as well. Then we have a polar form where our angle is expressed in pi radians. Then we have polar form with an angle expressed in radians. And then lastly, we have polar form with an angle expressed in degrees, which is how I typically want to represent voltages and currents. So this is the option that I'm going to choose. And then it converts everything exactly of the form that I'm looking for. So MathCAD can automatically spit the answer out in the form we want it to, just like our calculators. We just have to know how to tell it to do so. And that is all buried inside this one little menu. All right, so that was nodal analysis using complex numbers. When you're doing mesh analysis, the only thing I can really tell you that would be different is pay very, very close attention. So when you're multiplying your currents times your impedances, make sure that you are explicitly multiplying. It's very easy for MathCAD to interpret things in parentheses as a function of something else as opposed to a multiplication operation if you don't explicitly tell it to multiply. So that is the largest place that I see errors from you students is you don't tell it exactly, hey, multiply these two things, and it tries to interpret one thing as a function of the other thing. Okay. All right, so any questions on using MathCAD with complex numbers or just MathCAD in general? I know I went through that pretty quickly, but you guys have hopefully been using MathCAD for the bulk of this class. So yeah.
Whenever you put in J, you're just typing the letter J, right?
That is correct.
-1.
Yes, but only, so just to be clear here, if I did J5, that italices J is not the J that I'm looking for. So it is not interpreting that correctly. So that's why I'm having to do 5J. And then I have to explicitly multiply by my unit in order for it to calculate that or interpret that as an impedance of 5J with a unit of ohms. If I just did 5J capital omega, it's lumping that J omega together as some new undefined variable that's going to cause it to freak out. So that's why it's so important to explicitly multiply our units when dealing with complex numbers. Because MathCAD is really good at what it does, but it is really terrible at inferring what we want it to do unless we tell it exactly what to do. Anything else? All right, so is there any questions, anything about circuit analysis in the steady state sinusoidals or sort of in the frequency domain that you guys want me to review in person since I wasn't here on Monday, or are we good to work on the lab? All right, work on the lab.